right. Okay. Hello everyone. Welcome to Ferdinand Tutorials. Hello everyone. Welcome to Ferdinand Tutorials. I hope you are doing okay. Now, generally in this class, I want us to, continue from where we stopped in our last class. So, in our last class where we had our physics, we, stopped at electric circuit. Now, generally, I want us to look at, the electric circuit. Now, it's in this electric circuit that we'll try as much as possible to look at, electric current, and then we'll look at, resistors and capacitors. And when we are done there, we'll try as much as possible to look at expansivity, and from expansivity, we'll try as much as possible also to, look at wave equation, and then we'll explain some of the, classifications of wave, and we'll solve some questions that are related to wave. So I just want you to, stay with me. Any question you have, don't forget to, ask. I'll be here to answer. So generally, when we're talking about, the electric circuit, we say that the electric circuit. Now, I told you that, in this particular scenario, what we'll be looking at is we'll look at electric circuits. On the electric circuit, we try as much as possible to look at, the electric current. In this electric current, we'll look at some of the circuit elements like resistor, like capacitor. We'll also try as much as possible to, look at the calculations of both resistors and capacitors in series and in parallel. We also try as much as possible to look at expansivities. Begin to look at linear expansivity, volume expansivity, and area expansivity. I will, show you the formulas and the calculation. You understand, and how to solve questions that are related to them. Now, we also look at wave equation. In this particular video, we'll look at wave equation, and also try as much as possible to look at the classifications of waves. So I just want you to stay tuned. Don't be distracted. Try as much as possible to like the video so that it can be recommended for others too, and then share to someone that need to learn with you. So generally, when we're talking about electric circuit, we say that electric circuit is the complete path provided for the flow of, electric current. Are we there now? Now, the path that are provided for the flow of electric current. Now, the circuit usually consists of, how we call the circuit element. That's why when we are talking about electric circuit, we can have something like this. We have something like this. I'm just trying to, give, we can have something like this. Just work with me, please. And then we have something like this. Now, this is more like what we call a rheostat. So I have something like this. I can have, this is my battery. Let me add this as my battery. And then I can have this as my key. Together now. And then I have something like this. So let's say this is my R resistor. This is my resistor. This is my rheostat. Now this can be a conducting wire, right? This can be a key. A key is usually off and on, right? Or if you don't call it key, you call it a switch. And this can be a battery. If you don't call it battery, you can also mention a cell. And this is called what? An ammeter. Now, what is an ammeter? Ammeter is a circuit element that we use to, try as much as possible to measure an electric current. Now we have what we call ammeter, we have voltmeter, we have galvanometer. Now when we're talking about ammeter is a circuit element that we use to measure an electric current. Voltmeter is a circuit. Look at ammeter. This is the spelling of ammeter. This is ammeter, right? We have voltmeter and we have galvanometer. Are we together now? And we have what? Galvanometer. Now, I said that when we're talking about ammeter is a circuit element that we use to measure the what? The amount of electric current. We use it to measure the what? Amount of electric current. Now, we have what we call a voltmeter. A voltmeter is also a circuit element. In this scenario, we don't use it to measure the amount of electric current. We use it to measure the amount of voltage. I would know voltage in a particular electric circuit. Galvanometer in this scenario is generally used to, measure a small amount of what? A small amount of electric current. Are we together now? So in this particular circuit element, when they are joined together like this, we call it what? An electric circuit. So if I want to increase maybe this particular combination, I'll just add here, this voltmeter, because voltmeter is usually connected in parallel to the electric circuit, while ammeter is connected in series to the electric circuit. So this is a typical example of what? Electric circuit. Are we together now? So in every circuit, it must consist of a battery, which is, what provides the energy. We have a switch or a key to start or stop the current flow. We also have a voltmeter, which is this, which we usually use to measure the PD or potential difference. Are we there now? And we have the resistor, rheostat, and all that to just adjust, are we there now, the flow of this particular electric current. So generally, this is a typical example of, electric circuit. So, but in this electric circuit, I want us to look at what we call a resistor. Are we there now? A resistor, R-E-S-I-S-T-O-R, a resistor. Now, what is a resistor? Generally, a resistor is an electrical component, are we there now, that tries as much as possible to, limit the regulation of the flow of electric current in an electronic circuit or electric circuit. Are we there now? So a resistor is also a circuit element. Are we there now? A resistor is also what? A circuit element. So, but in this scenario now, what we are focused on generally is this. We're saying that, in every particular circuit element, or in every particular electronic circuit or electric circuit, we must have what we call what? A resistor. We must have what we call what? A resistor. Now, generally, we have different, arrangement of resistors in an electric circuit. And we there now, we have different arrangement of resistors in an electric circuit. There may be more than one resistor in every electric circuit. Are we there now? And as such, it can either be connected in, we can have resistor connected in series and another connected in what? This is connected in parallel. Are we there now? So when we have more than one resistor in a particular circuit, now how do we arrange it? Do we arrange it in parallel or in series? Are we there now? It's dependent on the particular electric circuit. So, but when we have a resistor in series, how do we calculate the total resistance? When we have resistors in parallel, how do we calculate the total resistance? So when we have resistors in series or resistors are said to be in series when they are arranged end to end, are we there now, to each other. Say for example, I can have something like this. I can have another something like this. Are we there now? These are typical examples of what? Resistors in series. They are connected end to end to each other. So this can be R1, R2, R3. Are we there now? So if I want to calculate my effective resistance, my formula for effective resistance will be REFF is equal to R1 plus R2 plus R3 plus Rn. Are we there now? That's my effective resistors in what? In series. This is series, serial connection. serial connection. Are we there now? Now, if I have my resistors in parallel, resistors are supposed to be arranged in parallel when they are connected side by side to each other. Are we there now? Resistors are said to be in parallel when they are arranged what? Side by side to each other. So we can have something like this. 1 over R EFF will now be equal to 1 over R1 plus 1 over plus 1 over R2 plus 1 over R3 plus 1 over R4 plus 1 over Rn. Are we there now? That's how to calculate what? Effective resistance in parallel. Now, the other one is in series. This is serial connection. This is parallel connection. And in parallel connection, this is what we have. Something like this. Something like this. Right there now. So, this is what we are looking at. So, this is, something like this. So, I can have here R1, R2, and then R3. Okay, now, so this is how to calculate a serial connection and what? A parallel connection. Now, in most cases, I can give you, say, example 1. Let's look at example 1 in this resistor before we continue. In example 1, E1, I can have, say, the resistor of resistance, the resistor of resistance 1 ohm, 2 ohm, and 4 ohms are connected in series. Find the total or the equivalent. Find the equivalent resistance of the combination. So solution, what are we going to do? What we are going to do is I will try as much as possible to solve the question. Now, to solve the question, we are going to say that we have 3 resistors, right? So what's the formula for resistance in series? We say REFF will be equal to R1 plus R2 plus R3, right? Plus Rn. How many resistors do we have here? 1, 2, and 3. So there are 3. So we say REFF will be equal to 1 plus, the first resistor is 1 ohm, the second one is 2 ohms plus 2, the third one is 4 ohms plus 4. So we are going to have 1 plus 2 is 3, 3 plus 4, 7 ohms. So the total resistance here is what? 7 ohms. Now we can also have this one, another example, something like this. They can say 2 resistors, 4 ohms and 2 ohms are arranged in parallel, calculate the total effective resistance. You also use solution. In this scenario now, you use solution, and then you say 1 over REFF will be equal to 1 over R1 plus 1 over R2, because there are only 2 resistors, have you? So you say, anywhere you see R1, you put 1 over 4 plus 1 over 2. You calculate, you say 1 over REFF will be equal to, what's the LCM of 4 and 2? LCM of 4 and 2 still remains 4, right? So you say, here we have 4 into itself, 1 times 1, plus 4 into here, 2 times 1, 2. So plus 2 will be equal to 3 over 4. Are we there now? So that means 1 over REFF is equal to what? 3 over 4. Therefore, REFF will be equal to 4 over 3. Are we there now? Ohms. This is the effective resistance. Now, if you check the option, you now divide this. If the options are in decimal, not in fraction, you have to divide this to get your answer. So we are done with arrangement of resistors. There are other questions you can see from your past question. Now, the next thing I want to teach you is internal resistance of a cell. 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 Now, when we're talking about internal resistance of a cell, internal resistance of a cell is represented with small letter r. Now? Is represented with what? Small letter r. Total resistance is represented with capital letter R. This capital letter R is also called external resistance. While small letter r is called what? Internal resistance. So we say that internal resistance of a cell, small r of a cell, is the opposition now to the current flow offered by the what? Offered by the chemicals between the poles of the cell. Are we there now? So we say that internal resistance, that means the maximum current that can be supplied by the cell of a given what? Of a given EMF. Look at how we usually solve it. We say that we use the formula I, which is current, is equal to EMF all over external resistance plus what? Internal resistance. Are we there now? Where I is equal to current in amperes. Are we there now? Current in what? In amperes. Close. And then E is equal to electromotive force, EMF, in volts. In volts. Are we together now? Now, small r is equal to what? Internal resistance. Internal resistance. Internal resistance is also in what? Internal resistance is in ohms. Are we there now? And then capital R is what? External resistance. Are we there now? External resistance. So whenever we have questions related to internal resistance, we use the formula I is equal to E all over what? R, capital letter R plus small letter what? Plus small letter r. Okay. Now, I want us to try as much as possible to solve questions that are related to this particular stuff. Now, already, we can solve questions. Say, let's use this particular example. Example 1. Example 1. We say, a cell can supply a current of 0.80 ampere. Are we there now? Through an external resistance of 5 ohms. Calculate the internal resistance. Calculate the internal resistance. With an EMF of 7.5 V. Now, remember, we use the formula. We say solution. We use the formula I, go back. You say I is equal to E all over R plus small r. Then you look at the parameters. What is E? E is equal to 7.5 V. Abi, that's what was given in the question. E is what? 7.5 V. Then you look at current. What is our I? I is 0.80 ampere. What else did they give us there? They gave us external resistance, capital letter R, as what? 5 ohms. And they're asking me to solve for my what? Small letter r, which is what? Unknown. So I will use the formula. I will say I is equal to E all over R plus I. Anyway, I see I, what will I put? I'll put 0.80 is equal to, anyway, I see capital E, what will I put? 7.5 all over. Anyway, I see capital letter R, what will I put? 5 ohms. I will then plus small r. I will do what? I will cross multiply. I will say that 7.5 is equal to 0.8 all in bracket 5 plus r. Are we together now? So I will say 7.5 is equal to, I will use my calculator, 0.8 times 5. Anything it gives me, I'll write it down plus, I will use that particular stuff to do 0.8r. I will then I will now make 0.8r the subject of the formula. Say for instance, if 0.8 times 5, I don't have a useful scientific calculator here, I would have used it to calculate, but you can use 0.8 times 5. Anything it gives you, that will, give you an answer. Let's say 0.8 times 5. Let's use 4. Let me just assume 4. Please be advised that, I'm just formulating a value. So let's say this is 4. So what I will do here is I will collect like that. I will say CLT. I will then this one comes over here. I will have 7.5. If it crosses over, I change plus to minus. So minus 4 is equal to 0.8r. Anything, let's say this is 3. 3 equals 0.8r. So the r will be equal to what? 3 over 0.8, which is what? The answer as my what? Internal resistance, always in what? In ohms. I would then, so that is that about, internal resistance. Now, generally also, we usually solve for loss voltage. Loss voltage is usually small letter V, loss voltage. Then we have what we call loss voltage, just in case you see questions like this. Loss voltage is small letter V. Now, loss voltage can be defined as a potential drop across the internal resistance. So, loss voltage is more like, the voltage of the internal resistance, while EMF is the voltage of the what? External resistance. So, loss voltage, we say that loss voltage mathematically is equal to V is equal to what? IR, just like Ohm's law. And then this is, the mathematical expression. And this particular small r is internal resistance. Are we together now? The small r is what? For internal resistance. And I here is what? Is the current. Are we together now? So that is generally how to, solve this particular question. Now, I want us to try as much as possible to look at, what we mentioned by expansivity. Because what I was explaining something, I mentioned about expansivity, and I told you that, I want us to look at, expansivity and then look at the types of expansivity. Now, first of all, when we mention about thermal expansivity, I hope you're following, right? If you have any question, please don't forget to ask. I'm here to answer all your questions as much as possible. Okay. Now, I want us to look at the thermal expansivity. Thermal expansivity. Thermal expansivity. Now, when we're talking about thermal expansivity, expansivity is more like expansion. Thermal is what? Temperature. So we're talking about temperature expanding a particular body. Temperature, expanding a particular substance, a particular medium. Are we together now? So when substances are heated, there is high probability that they usually what? Expand. Are we there now? Instead of the size of the object to contract, the size of the object usually what? Expands. Now, there are 3 important types of this particular thermal expansivity. We have what we call the first one. We have linear expansivity. Linear expansivity. Oh, there now. We have the second one. We have area expansivity. Area expansivity. And then we have the third one, volume expansivity. Now, when we are done with this expansivity, we'll enter into waves. So don't sleep, be awake, so that you get what we are talking about here. Now, in this scenario, now when we're talking about linear expansivity, now when we're talking about linear expansivity, we are generally focused on expansion of substance by increase in length, per unit length, per degree, degree rise in temperature. And that is why in linear expansivity is denoted as what? As alpha. Linear expansivity is denoted as what? As alpha. It is given as increase in length all over original length times temperature rise, temp rise. So when we're talking about increase in length, for us to increase in length, we are talking about from 2 to 1 or from 1 to 2. That's increase. Say someone is increasing in growth. Is from growth, if from maybe 2 years they move to 3 years. From 3 years they move to 4 years. So in increase in length, now we're talking about alpha. Remember, when we talk about alpha is linear expansivity. So linear expansivity is equal to L2 minus L1, because that's increase in length all over original length. We're talking about original length. Original length is still L1. Now times, what is temperature rise? Temperature rise is also theta 2 minus what? Theta 1. So we're going to have theta 2 minus what? Theta 1. Specifically, that's what it's all about. So where alpha is linear expansivity, so L1 will be equal to length, maybe we say length of objects at temperature 1, or we say L1 is equal to length of object at theta 1. L2 will be equal to length of object or length of metal at theta 2. Are we together now? Now, we can now look at what are the examples. Are we together now? And if we look at theta 1 and theta 2, already know what theta 1 is now. Theta 2 is the final temperature. Theta 1 is initial temperature. Are we together now? So that is that. Now we can look at example. Let's look at this particular example. Example 1. Now they say a copper rod with length, where length or whose length are 30 degrees C. Whose length at, okay, the question is at, whose length at 30 degrees C is 10 meter, 10.0 meter, is heated to 50 degrees C. Find this new length. Find this new length. Take alpha of copper as 0.0000. How many 0? 1, 2, 3, 4. Okay, 4017 per Kelvin. So that is a particular question we are going to solve. Now look at this particular specific question. It says a copper rod whose length or wear length at 30 degrees C is 10.0 meter is heated to 50 degrees C. Find its new length. Take alpha of copper. Remember, when we're talking about this alpha is what? Linear expansivity, right? Alpha is what? Linear expansivity. So in this scenario now, what are we going to do? What we are going to do is that we're going to come back. So, okay, look at the formula. Solution. Alpha is equal to L2 minus L1 all over L1 bracket theta 2 minus what? Minus theta 1. So let's look at the parameters that we're given. They say a copper rod where length at. That means Theta 1 is what? Is 30 degree. Theta 1 is what? 30 degree. So what we're going to do is that we're going to say theta 1 is what? 30 degrees C. Are we there now? And theta 2, what is theta 2? Theta 2 is going to be what? 50 degrees C. Are we there now? And then we'll come here, we'll look at the length. At 30 degrees C, which length do we have? 10 meters. So that means theta 1 is 30 degree. And L1 is what? 10.0 meter. Are we there now? Now, L2, did they give us L2? L2 is what? Unknown. Are we there now? So that means what we are looking for is our L2. Because it says, is it to find its new length? Its new length will be, the final length. So what we're going to do, we're going to use alpha. Are we there now? Alpha will be equal to, anywhere we see alpha, what are we going to put now? We're going to say alpha is equal to 0.000017 per Kelvin. So what we're going to do here, we're going to come here, we say, anyway, I see alpha, I'll put 0.000017 is equal to L2 minus 10 meter all over 10 meter bracket. Now, this is in degree C. If you look at this particular alpha was a per Kelvin. Are we there now? So I'm at liberty to convert that particular degree to Kelvin. Are we there now? I'm at liberty to convert this particular degree to Kelvin. But in my exam, I might not have time. Even at that, I can still try and solve and say, okay, even though we say 50 minus what? Minus 30. So I'm going to say 0.000017 will be equal to L2 minus 10 all over 10 bracket 20. You say equal to L2 minus 10 all over 10 times 20. I have 200. Are we together now? So I can easily say 0.000017 is equal to L2 minus 10 over 200. I can cross multiply. We say L2 minus 10 is equal to 200 times 0.000017. So that means L2 will be equal to anything I have here plus 10. I will say bracket 200 times 0.000017 plus 10. Are we there now? That will be my answer. L2 will be equal to anything I have here in meters. Are we together now? That is that. That is linear expansivity. Are we there now? I just solved for my what? For my L2. Now, if I also come for my area expansivity is pretty much, simpler. It's almost, the same formula too. Are we there now? Now, in area expansivity, what I'm going to use, area expansivity is represented with beta. Area expansivity is represented with what? With beta. So I'm going to say, anywhere I see beta, that is my what? My area expansivity. I'm going to say A2, are we there now? Minus A1. Remember the way? All over A1, open bracket, theta 2 minus what? Theta 1. More like the same formula too. Are we together now? So I can easily say, for me to calculate my A2, I'll just say A2, which is, the stuff I did. A2 will be equal to A1 bracket 1 plus, beta times theta. Are we there now? So it is almost easier. And for you to calculate your theta is given as theta 2 minus what? Minus theta 1. Are we there now? So you can pretty much use this formula to get your area expansivity. And then for your volume expansivity, which is, if you don't call it volume, you call it cubic. For your volume expansivity, this is area. Beware. Now for your volume expansivity, we are going to use gamma. Are we there now? We use gamma equals also V2 minus V1 all over V1, open bracket, theta 2 minus theta 1. Or you say V2 minus V1 over V1 bracket theta, where theta is equal to theta 2 minus what? Theta 1. V2 is final volume, V1 is initial volume. Or you say V2 is volume for temperature 2, V1 is volume for temperature 1. Are we there now? And for you to get your V2, you can literally say V2 will be equal to V1, open bracket, 1 plus, beta times what? Times theta. Are we there now? So you say V1, open bracket, 1 plus beta theta. Are we there now? That's how to find it. You can also say L2, which is what I just solved. L2 is equal to L1 bracket 1 plus alpha theta. Are we there now? That's how to find your, final length, final volume, are we there now? Final area. Use these formulas and you can get your answer as easy as possible. Are we there now? Now, I'll give you a work that you can try. Are we there now? Try using this particular formula. Now, the linear expansivity of the material. Now, let's solve this question. Say, let me give assignment or classwork. Solve it and drop the answer in the comment box. I want everybody to try it. Say the linear expansivity how do you know, of the material of a cube is 12 times 10 raised to the power minus 6 per Kelvin. They're giving us a linear expansivity. Are we there now? If the length of the cube is 10 cm, if the length of the cube is 10 cm, find the area of one face of the cube, of one face of the cube, and the volume of the cube, when its temperature is raised by 30 Kelvin. Now let me give you a clue. Now in questions like this, they gave us linear expansivity, which is what? Which is my alpha. Are we there now? Is already stated. Now they say if the length of the cube is 10 cm, find the area of one face of the cube and the volume of the cube when its temperature is raised by 30 Kelvin. Now note, I hope you can see what I'm writing. Now note that, beta, what is beta? Beta is what? Area expansivity. Beta is equal to 2 times linear expansivity. And volume expansivity, which is gamma, is equal to 3 times what? Linear expansivity. So this is 2 alpha. This is what? 3 alpha. So if the length of the cube, they say find the area of one face of the cube and the volume of the cube when its temperature is raised. Are we there now? So what they're asking you is find the volume, that's the V2 and the what? And the A2. Are we together? Can you solve that? Of course you can. Are we together now? Of course you can. So try and solve it and let me know what you think. Are we there now? So I've given you the expansivity. So try and solve and let me know what you think. I'll be in the comment section. Anybody that get the answer right will win a prize. Are we together now? All right. But if you can't solve it, I will still solve it in the correction. Maybe next time I'm teaching physics, that's the first thing we'll look at. So we're done here. I want us to try as much as possible now to, look at waves. I want us to look at, waves. Now, generally, when we are talking about, waves and wave equation, there are important concepts I want you to, learn and understand. When we're talking about waves, that's the topic, waves. Now, when we're talking about wave, we say that wave is a disturbance or oscillation. Wave is what? A disturbance or oscillation that travels through space and matter, transferring energy from one point to another without the transport of what? Of matter. Without the transport of what? Of matter. Now, in this scenario now, what we are trying to say is that the particles of the medium do not travel with what? Do not travel with the wave. Now, those particles simply oscillate around a fixed point. They simply oscillate around what? Around a fixed point. Are we together now? That's wave. And now we have what we call classifications of wave. Classifications of what? Of waves. Waves are generally classified into two. Number A, based on medium of propagation. Based on medium of propagation. Based on what? Medium of what? Propagation. Number B, based on direction of particle vibration. Based on direction of particle vibration. Are we together now? Now, if we look at number A, based on medium of propagation. Based on medium of propagation, they are into two. We have what we call what? We have the first one, which is the mechanical wave. Are we there now? We have mechanical wave. Mechanical wave. Now, what is mechanical wave? Number one, mechanical wave. Now, we say that a mechanical wave, what we are generally focused on, we're saying that it requires a material medium for its transmission. It requires what? This particular type of wave. I told you that classification of wave based on medium of propagation and based on direction of particles of vibration. Now, under mechanical wave, which is based on medium of propagation, it requires what? It requires a material medium. It requires a medium. Now, the medium we're talking about are solid, liquid, or gas to propagate. Are we there now? Now, when we're talking about mechanical wave, they cannot travel through a vacuum. Are we there now? So, examples of mechanical wave are sound wave, water waves. Are we there now? Now, water waves. We also have seismic waves. That is that. Now, number two is what we call what? Electromagnetic wave. Electromagnetic waves. If we say that, a mechanical wave requires a material medium, now electromagnetic wave will be the opposite. They do not require a medium. Are we there now? Now, they can travel through a vacuum because in mechanical wave cannot travel through a vacuum. Understand the difference. In mechanical wave requires a material medium to propagate and as such cannot travel through what? A vacuum. Meanwhile, in electromagnetic wave do not require a material medium and as such can travel through a material and as such can travel through a what? A vacuum. Examples of electromagnetic waves, we have what we call the light waves. We have light wave. We have X-rays. X-rays. X-rays is an example of what? Of electromagnetic wave. We have X-rays. We have radio waves. And we also have what? Microwaves. Those are examples of mechanical and what? And electromagnetic wave. So we've explained based on what? Based on medium of propagation. Now I want us to look at based on what? Particles of vibration. Based on particles of vibration. Now under based on particles of vibration, based on particles of vibration are divided into two. Based on particles of vibration. Based on direction of particles of vibration. Based on direction of particles of vibration, they are divided into two. We have number A, transverse wave.
transverse what? Wave. Let's look at it one after the other. Now, when we're talking about transverse wave, we say that transverse wave, the particles of the medium vibrate perpendicular to the direction of the wave. Particles of the wave, or particles of the medium, vibrate perpendicular to the direction of the wave. Particles of the medium vibrate perpendicular in the same direction, to the direction of the wave. Now, examples of transverse wave, we have what we call, your light waves. Light waves again. So that means light wave is both electromagnetic and transverse. So light waves, water waves, and water waves is both mechanical and also transverse. Water waves, we also have waves on a string. Now we have the number B under the direction. Number B is what? Longitudinal waves. Longitudinal waves. Now, under longitudinal waves, we are saying that particles of the medium travel parallel to the direction of the wave. Particles of the medium travel parallel to the direction of the wave. Examples of longitudinal waves, we are looking at something like, your sound waves. Compression in a spring. Compression in a spring, not string now. There's a difference between spring and string. Compression in a spring. Spring balance, like spring. And we have the number next, based on direction of particles of vibration, which is called what? Surface waves. Surface waves. I decided to add this one too. Now, under surface waves, it combines, both that of the transverse and longitudinal waves. They travel along the surface of the medium. Example is ocean waves. Ocean what? Ocean waves. Now, there are important terms associated with this particular wave before we look at wave equation. Wave equation will be the last thing we'll look at in this particular class. So there are important terms associated with, waves. Are we together now? But let me first of all look at a specific diagram of a wave. Now, if I have something like this, look up. I'm going to have something like this. Now, look up. This particular uppermost part of a particular wave, this is the direction of a wave, right? This is the movement. It's moving from left to right. This particular upper part is called what? A crest. It's called what? Crest. The above region is called what? Crest. Now, this downward part, remember, they must be on the same line. This downward part is called the what? The trough. 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 Now, the distance between two successful crests is called what? It's called my wavelength, which is lambda. The distance between these two successful crests is called what? A wavelength, which is lambda. And the distance between these two successful troughs too is called what? My wavelength too, which is lambda. Are we together now? So let's look at the terms associated with this specific man called waves. Terms associated with waves. Are we there? Important terms associated with waves. Now look at the terms associated. Please, if you have any question, don't forget to ask. Associated with waves. Now the first one is crest, which I just explained. I said that crest is the highest point. Crest is the highest point of a transverse wave. Is the highest point of a transverse wave. Are we there now? We have number 2, trough. I just showed you a trough. It's the lowest point also. This is the lowest point. This is the lowest point of the what? Transverse wave. Of the transverse wave. Now we have what we call a compression. These are important terms I want you to know. It's a region in a longitudinal wave. This is a region in a longitudinal wave. A longitudinal wave. Are we there now? Where particles are closest to each other. Where particles are closest to each other. Where particles are what? Are closest to each other. Are we together now? Now we also have another particular stuff called refraction. Refraction. Now refraction is the opposite of what? Compression. Are we there now? Now it's also a region where particles are further apart from each other. Are we there now? Opposite of what? Opposite of compression. Opposite of what? Compression. Now the number 5th is what I call wavelength. Are we there now? Now wavelength is represented as what? As lambda. So it's the distance between two successful crests. This is the distance I hope you can see what I'm writing though. This is the distance between two successive crests or trough in this scenario. Are we there now? Now move to amplitude. Now I forgot to show you what amplitude is. Now this particular distance between this particular point here, are we there now, and this particular point of origin is called what? My amplitude. From here, okay, you can't see it. From here to here, the distance between here and here is called what? Amplitude. Are we there now? All right, back to business. So I was saying, I say amplitude. And what then is amplitude? Is the maximum displacement maximum displacement are we there now? From its rest position. From its rest position. And amplitude is represented with what? Capital A. Are we there now? Now, the next one I want us to look at is frequency. Frequency is represented with F. Are we there now? It's the number of complete circles that pass a point in 1 second. The number of complete circles that pass a point. Are we there now? In 1 second. In 1 second. We also have what we call period. Period is represented with capital T. Are we there now? Is the time taken for one complete wave to pass a point. Is the time taken for one complete wave to pass a point. Are we there now? To pass a point. Are we together now? Generally, we say that T is equal to 1 over what? 1 over F. And as such, F is also equals 1 over T. Are we there now? This is period. This is, frequency. Are we together now? Now we'll move on to the number next, which is what? Wavelength. Now wavelength. This is wavelength. Wavelength is represented with what? Is represented with V. Are we there now? Is the speed. This is the speed. Are we there now? At which wave travels through the medium. At which wave travels through the medium. Are we there now? So we use V is equal to F lambda. F times what? F times lambda. Then that's the formula for V, where F is frequency, lambda is what? The wavelength. Are we together now? Lambda is the what? Is the wavelength. Now let's look at equations of wave. Equations of what? Of wave. Please go through all these things we've been looking at. Identify if you have any particular issue from what I've been explaining. Is there any particular concept you still don't understand, or you're trying to find difficult to follow suit? Please let me know. Let me know where I can come in or not. Are we together now? Okay. All right. Now equations of waves. Equations of wave. This is the equation. We say y is equal to a sine kx plus omega t. Are we there now? This is when the wave is moving from left to right. Are we there now? Moving, from left to right. Are we together now? So it is specifically positive at this particular angle. That's why we have positive here. So in this scenario now, what we're going to do is that we're going to say, a sine kx plus omega t, where k is the wave number. Now this particular k, which is the wave number, has a specific formula. K is equals 2 pi over what? Over lambda. 2 pi over what? Over lambda. Are we together now? And omega, which is the what? Angular velocity. Omega, I say k is wave number. Are we there now? Omega is equal to angular velocity. Angular velocity is equal to 2 pi f. So anywhere I see k, what will I put? 2 pi over lambda. So equation of wave can be rewritten as y is equal to a sine. Instead of putting k now, which is my wave number, I'm going to put 2 pi over lambda or x plus. Now instead of putting omega, what am I going to put here? I'm going to put what? 2 pi f. 2 pi f t. This is a typical equations of what? Of wave. Are we together now? Where y is equal to vertical distance. Vertical distance. Are we there now? In meter. A is equal to amplitude. Remember, amplitude of wave, also in meter. Are we together now? X is equal to horizontal distance or displacement in this scenario. Horizontal displacement. Are we there now? Lambda is equal to what? Wavelength. It should be in meter. Are we there now? T is equal to time in seconds. Are we there now? And then omega is equal to what? Angular velocity. Are we together now? So now let's try as much as possible to look for maybe one example. So look at this question. Question 1. Question 1. It said, given the progressive wave, given the progressive wave equation, y is equal to 2 sine, open bracket, 2000 pi t minus 0.5x. How then I say I? What is the frequency of the wave? What is the frequency of the wave? I. What is the amplitude? What is the amplitude? What is the amplitude? What is the word amplitude? Now let's rewrite this particular. Let's solve solution. What I'm going to do is I'm going to first of all write out my wave equation. Remember, my wave equation is equal to y is equal to a sine 2 pi x over lambda. I can say plus 2ft minus 2ft minus 2 pi ft. I'm still going in the same direction. Let me use plus 2 pi ft. Now, in this scenario, what happens is, the particular charge here does not affect anything. If you look at the equation they gave me, they say y is equal to, they didn't give a, they say y is equal to 2 sine, open bracket, 2000 pi t minus 0.5x. If I compare this particular question, what are they asking me to find? They're asking me to solve for frequency. They're asking me to solve for what? Frequency, which is f. So in this situation now, where do we usually see frequency? Frequency comes here where we have t. In my wave equation. So where do I have t here? I'm seeing here. So I'm going to compare. So comparing now, to find my frequency, I'm going to take this particular place where I have my t, because where I see frequency is where I have t, ft. So I'm going to say 2 pi ft will be equal to 2000, pi t. Pi will cancel pi. T will cancel t. So I'm going to have 2f is equal to, you can see what I'm doing here. 2f is equal to what? 2000. So f will be equal to 2000 over 2, which is equal to what? 1000. What's the unit of frequency? S. So I've solved the first question, which is calculating my frequency. Now, the second question that they ask us, they say, what is my amplitude? If I'm comparing this, I say a sine, 2 sine. That means my amplitude is what? 2, because amplitude comes before sine, and here we have 2 comes before sine. So my amplitude is equal to what? 2 meters. Are we together now? So I've solved question 1. Let's move on to question 2. Are we together now? I told you that this particular plus, some questions you see minus or plus, it doesn't really, affect any. This plus or minus is only trying to tell us if the wave is moving in the right hand side or the left hand side. It's just the direction of the wave. Are we together now? Okay. Now, question 2. Given the progressive wave equation, given the progressive wave equation, are we there now? Given the progressive wave equation, they say y is equal to 5 sine, open bracket, 2000 pi t minus 0.4x. Are we there now? Calculate the wavelength. Calculate the wavelength. Now, in this option, they gave A 12.4 meter, B 15.7 meter, C 17.5 meter, D 18.6 meters. So let's solve. They're asking us to calculate for wavelength. Remember, wavelength is what? Is lambda. Solution. Solution. Now, remember the equation of wave. I say y is equal to a sine, open bracket, 2 pi x over lambda, or here now, plus or minus 2 pi ft. So where can I see my lambda? This is lambda, which is wavelength, where we have x. So I will equate this particular part to where we have x. I will then now to calculate to make sure I get my lambda. So I will say 2 pi x over lambda is equal to 0.4x. X cancel x. So I have 2 pi over lambda is equal to 0.4. Cross multiply, I will have 0.4 lambda is equal to 2 pi. Are we together now? So I will say lambda will be equal to 2 pi over 4. Are we there now? 2 pi over 0.4 rather, not over 4. 2 pi over what? 0.4. What is pi? Pi is 3.142. So I will say 2 times 3.142 over 0.4. Are we following what we're doing here? So 2 times 3.142 over 0.4. So 2 times 3.142, that should be 6.28 something. So I would say my lambda will be equal to 6.284 all over 0.4. That should give me 15.71 meters. Are we together now? Which one do we have? 15.71. So I have 15.71 meters, which is this. So I will take it. That's my answer. I've calculated my what? My wavelength. Are we together now? I've calculated for my what? For my wavelength. Now let's solve one more question in this particular wave equation. Okay, they said the distance, number 3 question. The distance between two successive crests. Remember the definition I gave you. So between two successive crests of a wave is 15 cm, and the velocity and its velocity is 600 meters per second. Calculate the frequency. Calculate the frequency. They gave me option. Option A, 4.5 times 10 raised to power 5s. Option B, 4.0 times 10 raised to power 3s. Option C, 2.0 times 10 raised to power 4s. Option D, 4.5 times 10 raised to power 2s. Okay, let's calculate. Remember when we say distance between two successive crests of a wave, what do I call it? I call it what? A wavelength, which is lambda. So that means solution. They gave me lambda. Lambda as what? As 15 cm. And they gave me v, which is velocity at what? At 600 meter per second. So that means this one is in meter, this one is in cm. So what do? We convert cm to what? To meter. Converting cm to meter, we divide by 100. So I'm going to have 15 over 100. I'll move 1 and 2, 0.15 meters. Remember the formula. V is equal to what? F lambda. V is equal to what? F lambda. So to calculate my wavelength, I'm going to say therefore lambda will be equal to V over what? Over F. What is my V? Lambda will now be equal to, what is my V? My V is what? 600. What is my F? My F is what? Sorry, what am I saying? I'm calculating for frequency, right? So sorry for that, sorry. So V is equal to F lambda. So my F will be equal to V over lambda rather. So I'm going to say F will be equal to, anywhere I see V, what would I put now? 600. Anywhere I see lambda, what will I put? My lambda is my, 15 cm, which was converted to meter, 0.15, which is equal to what? What is my answer now? My answer is what? 4,000 hertz, which is the same thing as what? 4 times 10 raised to power 3 hertz. Answer. Number B is my answer. Are we together now? Are we together? So I've calculated it. Oh, I don't know if you're following what I'm doing here. Are you following at all? Do you have any particular question? Do you have any particular question? Do you have any particular question? I want to give you a classwork to do. Do it and share the answer with me in the comment box. Do it and share the answer with me in the comment box. Look at this question. I saw it in a past question. It says, this is number 4. I will not look at that. I will not use that as an example. So it's your classwork. It says, the progressive wave equation is given as y is equal to 15 sine 2 over 5 bracket 60t minus x. How do you know? What is its wavelength? What is its wavelength? My mind is telling me to solve this particular one, and then I give you another. This one you might think of it as very hard. What do you think? Should I solve it? What is its wavelength? What do you think? I should solve it, right? Okay, let me solve it. Let me solve it since my mind is already telling me to solve. It might be a bit difficult for you. So look at this particular question. They say, what is its wavelength? This is the particular wave equation. Y is equal to 15 sine 2 over 5 bracket 60t minus x. Now for me to solve, I will do solution. First of all, let's make the equation to be better, because in my wave equation is y is equal to a sine, I would then open bracket 2 pi x over lambda, I would then plus 2 pi ft. So it is not really, a good equation here, because in my wave equation is a sine open bracket, but I'm having 15 sine 2 over 5 before opening bracket. So that means 2 over 5 will multiply everything in this bracket. So I'm going to now have y will be equal to 15 sine, are we together now? 2 over 5 times 60t. I'm going to have, open bracket, 2 times 60t over 5 minus 2 times x over 5, which is the same thing as y will be equal to 15 sine bracket 2 times 60, 120t over 5 minus 2x over 5. You're getting what we are doing here? So I've already, got to my equation from the question. So what did they ask me to find? They asked me to find what? Wavelength. What is wavelength? Lambda. Are we together now? So that means I'm going to have something like this. My wave equation, y is equal to a sine, open bracket, 2 pi x over lambda plus or minus 2 pi ft, close the bracket. Meanwhile, the equation I have y is equal to 15 sine, open bracket, 120t over 5 minus 2x over 5. Now, where can I see my lambda? Where I have x, abi? This is lambda, x, lambda down here. So I'm going to say 2 pi x over lambda will be equal to 2x over 5. Are we together now? So x cancel x. Are we there now? So I'm going to have 2 pi over lambda is equal to 2 over 5. Are we together now? So I'll cross multiply. I will say 2 lambda is equal to 10 pi, because 5 times 2 is what? Is 10. So I'm going to say lambda will be equal to 10 pi over what? Over 2. What is 10 pi? 10 pi is what? 10 times 3.142 over what? Over 2. 10 times 3.142, I'm going to have, probably something within, okay, let me do 2 into here, 1. 2 into this, I'm going to have 5. 5 times 3.142, I should have 15.776 meter. I think it should be. Now, if you look at the option they gave, in the question was A, 60 meter, B, 15 meter, C, 5 meter, D, 2 meter. So I'm going with what? 15 meter, even though closest here should be 16 meter. Okay, this is 15.71 though. So I'm going with what? 15 meter. So that is that about the wave equation. I've solved question relating to wave equation. So I want you to try as much as possible to ask your questions in the comment box. But before we round off, I want to say something about capacitors. I want to say something about capacitors. Now, capacitors generally, what they do is that they help us. They are electric circuits or circuit elements that we use to store charges. Also, we have arrangement of capacitors. Capacitors can also be arranged in series and in what? And in parallel. Capacitors can be arranged in series and also in what? In parallel. They are more like opposites of what? Of resistors. If you remember resistors, in resistors, note, resistors, to calculate resistors in series, note, resistors in series was given as R is equal to R1 plus R2 plus R3 plus Rn. Now, for capacitors in series, what we are going to do here is that we are going to do inverse of resistors in series, which is 1 over CEFF is equal to capacitors in series. This is the formula now. 1 over CEFF equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over Cn. Are we there now? And remember, for resistors in parallel, resistors in parallel is going to be, remember, 1 over REFF is equal to 1 over R1 plus 1 over R2 plus 1 over what? R3 upon 1 over Rn. So that means in capacitors in parallel now, capacitors in parallel will also be a reverse equation. I'm going to have something like this. CEFF is equal to C1 plus C2 plus C3 plus Cn. So to calculate my capacitors in series, I will use the formula for resistors in parallel. To calculate my capacitors in parallel, I will use the formula of my resistors in series. So they are inverse of each other. Now, we usually have energy in a capacitor. To calculate the energy in a capacitor or work done by a capacitor, we usually use the formula E is equal to 1 over 2 CV square. Are we there now? 1 over 2 what? CV square. Where C is the effective capacitance, V is the what? Is the voltage. Anything you get, your answer must be what? In joules. Your answer must be in what? In joules. Are we together now? That is how to solve questions related to capacitors and capacitance. So I want you to solve questions relating to this particular, equations I've been able to solve in this particular class, and then, study them, put them into practice. If you have any question, don't forget to let me know. That is what I'm here to do. I'm here to try as much as possible to guide you, provide directions to you, and make you to understand this different concept of what we're doing here. Are we together now? So I hope this particular class has helped you to understand, the difference between resistors in series and resistors in parallel, capacitors in series and capacitors in parallel, and also help you to understand about, electric current. Are we there now? Electric current, very, very important. Are we together now? We begin to look at quantity of electricity,
In many questions, in your past question, you begin to see questions relating to what? Quantity of electricity, where we say Q is equal to what? IT. And I hope you've understood the formulas for solving wave equation. Are we together now? I have mentioned the divisions of wave. Are we there now? How waves are classified. Are we there? Based on their medium of propagation and based on the direction. Are we there now? Of the propagation. Are we together? Where we have mechanical, electromagnetic, transverse, and what? Longitudinal, and also surface. So thank you all for watching. I want to see you again in my next, online class, next live session. And if you have your question, don't forget to drop in the comment section. I'll be here to answer. Thank you for your time. Bye.